In this video we'll be learning all about Kirchhoff's current law. Gustav Kirchhoff was a German physicist of the mid to late 1800s. He played a paramount role in the modern understanding of fundamentals of electrical circuits, as well as spectroscopy and blackbody radiation. Perhaps one of his most significant contributions was the development of Kirchhoff's current and voltage laws in 1845. These laws built upon the work of other notable physicists George Ohm and James Maxwell, and provide a basis for the understanding of properties of current and voltage in both DC and AC circuits. In this video we'll be focusing on Kirchhoff's first law, that is, Kirchhoff's current law. Kirchhoff's current law states that the current flowing into a node must be equal to the current flowing out of the node, thus meaning that the current is conserved throughout the closed circuit. This can be expressed using the formula: the sum of the current into the node equals the sum of the current out of the node. Keeping this in mind, we can see that in this example, I1 and I2 which go into the node are equal to I3 and I4 which go out of the node. Another way to understand this is by picturing a flowing river. Even if the river diverges into two paths, the total amount of water stays the same. This is also true if one branch of the river is larger than the other. Although there are now different volumes of water in each branch, the total volume remains the same. See how this compares to the diagram on the right? Although the current in the individual branches are not equal due to differing resistance, the total current in the circuit never changes. Current cannot be depleted, and the total quantity remains the same throughout the circuit regardless of the resistors or other electronic components. This can clearly be seen in the parallel circuit example. Using Ohm's law, we can calculate the total current in the circuit to be 7.5 amps. Similarly, the current through R1 can be calculated using Ohm's law. This was found to be 5 amps. The same can be done for the second resistor, resulting in 2.5 amps. As we can see, due to the different resistors used, the current in these branches are not equal. When we add them together, however, the resultant current is equal to the calculated total current of 7.5 amps, thus confirming Kirchhoff's current law. Knowing the current in a circuit through the implementation of Kirchhoff's current law is crucial for designing electronic products which work and that are safe to use. For this reason, Kirchhoff's current law is of great significance and use in circuit analysis.